down the list here to some other sort of chain rule styles. All right, so our most basic type of chain rule problem is when we've got a quantity raised to a positive power, like 2x minus 4 all to the fifth, or even a more complicated expression like 3x minus 4x squared all to the fifth. I don't know what I was in love with fifth powers here when I was writing this. So derivative using chain rule, 5 times the quantity 2x minus 4 all to the fourth power times an additional 2. You can stop right there. That's an absolutely fine derivative. No reason to do anything to it unless, for some reason, you want to kind of get the constant factors together and make that a 10. That's acceptable. You're not going to be able to do anything to the stuff in the parentheses. It's still raised to the fourth power, and so that kind of blocks it off from anything getting distributed inside. If we expanded it out and then took the derivative, what we would get would be algebraically equivalent to what we've written here. They would not look the same until we did a lot of cosmetics work on it, but ultimately, term for term, they would be the same answer. All right, good on number 1? So number 2, not really any more complicated in the basic premise, but the chain aspect is an additional expression in this case. So not a constant in the chain, because the function inside here, when you have a linear function, you get a constant derivative. Here we had a partial, like a quadratic function, because I have a degree 2 power here. And so I end up with a linear function derivative. That's the additional portion of the chain. So that's where they really start to get kind of messy looking, is when this is more complicated of a function, the additional chain piece has a little bit more to it. Okay. If you did look this up, what you would see out in the world is a chain rule definition is anytime you would have f of g of x, one function of another, the derivative is equal to the derivative of the f function around the g, and then times the derivative of the g, which is the inside. What I have done, since we're only talking about one kind of f function, which is basically having something raised to a power, we're only looking at this one specific type of chain rule problem. But if you Google it, or if you go on Khan Academy and you look up chain rule problems, you'll see a lot of different scenarios depending on what the f function is. Bringing trig functions in, like the sine of an x squared. If I do a trig of another trig, you can do the inside function might be trig. You can have natural logs, you can have e's, you can have all different combinations. We're kind of staying a little small because we're using a certain restricted group of functions for f and g, but we are taking the derivative of the outside. The derivative of something to the fifth is 5 something to the fourth, and then the inside something, its derivative tacked on the end. All right, 3 and 4 are related. They're both roots. This one would be 3x minus 7 to the 1/2 power. And this would be 7x cubed minus 5x to the 1/3 power. Okay. In both of these cases, expanding isn't really an option. There's not a plan for rewriting something that's to a square root, that's being square rooted like we can with something squared. But the chain rule will still apply. We'll bring the 1/2 down to the front. We'll keep the 3x minus 7. we'll put the negative 1/2 exponent on there because that's one less than the original. And then I'll multiply by a 3. Different scenarios might have us write this in a different form. If all we're going to do is plug a number into it, it's perfectly fine like this. Since we've got a calculator to utilize, it doesn't really matter if we have negative powers and things like that. Our calculators and things like Desmos handle those just fine. If we wanted to write this with positive powers, though, this would be using a little of our Algebra 2 / pre-calc. I would have a big fraction. The 3 would be in the numerator, because the 3 is kind of like a 3, well, it's not kind of like, is a 3 over 1. So the 3 would be the numerator element, the 2 would be in the denominator, and the 3x minus 7 to the negative 1/2 would mean I would have a root of that also in the denominator. Similar kind of construction on number 4. 1/3 comes out front. 7x cubed minus 5x in the parentheses. Negative 2/3 new exponent. Chain 21x squared minus 5. Once again, if we wanted to move some pieces around there, if we wanted to throw some stuff in a denominator, we could. I'm going to run out of room here, but I could. The 21x squared minus 5 would be up in the numerator. The 3 would be in the denominator. And then I would have a cube root of 7x cubed minus 5x all squared. This definitely, when we're starting to talk about doing mental math and evaluating things like this without any technology, there's a reason for writing it this way. When we've got technology to help us, it doesn't matter. Negative 2/3 power, your calculator doesn't care. It can do that. It's built to do that just as much as any power. So, you know, a 1 plugged in here, a 1 plugged in here, we could generate a number for this. All right, so 1 and 2, kind of basic. 3 and 4, roots, negative exponents. 5 and 6, actually not roots, oh yeah, but roots, and then we generated some negative exponents after we took our derivative. 5 and 6, kind of what they have in common is sort of that extra power, or excuse me, extra factor, sort of sitting in the front. Kind of like back when we would have a times x to the n. And just like that, those problems, this extra factor in the front, no big deal. You just kind of let him go along for the ride. So my 10 is there. I'll have my 3/5, my 3x minus 2 to the negative 2/5 times another 3. 2 common mistakes happen a lot on chain rule. One mistake is just not giving this a new exponent. Bringing this down and then just letting that be nothing, or a 1. Second thing is sort of chaining too soon, kind of doing this, but then also like changing this to a 3. And not just letting that sit through. Whatever's sitting in the parentheses in your original problem should be sitting in parentheses in your answer when you're doing a chain rule derivative. I'm going to squish number 6 over here. So this is number 5. So number 6, I would have the 12 and the negative 2 and the x minus 4 to a negative 3 times a 1. Now, this is a good example of where if we forgot a little bit about chain rule, it wouldn't hurt us. It also kinds of shows us that if we do a chain rule, even when you kind of don't need one, the only extra thing you're going to multiply by is a 1, and that's not going to change anything. So anytime you have something raised to a power, you can kind of think, oh, I'm going to, bring it down, blah, 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 and then times the derivative of the inside. It's just, if the inside is just an x, your derivative is just 1. Even when your inside is x minus 4, your derivative is just 1. It's not a huge change if you forget the change rule. It doesn't change anything at all. But it's good to remember the thinking. It's kind of like you're going to have to be able to recognize, like, oh, crap. Not that. There it is. Okay. What you have to be able to recognize is when you see something like this, you're like, oh, I've got a big, scary thing to a power. This is a chain rule problem. Just like I see a product and I know I need to do a product rule, or I see a quotient and I need to do a quotient. All right. The other thing I wanted to show you as we're working through some of these chain rule problems is oftentimes a chain rule might sneak in to another problem and actually make it a little easier. A good example of this is a quotient rule problem, like 7 and 8 are both quotient rule problems initially, with a constant numerator. Now let's talk about problem number 7. I'm actually going to come over here. So if I have 4 over 3x minus 2, and I decide I want to use quotient rule to find that derivative, okay, I can do that. My top is 4, so the derivative of that is 0. My denominator is 3x minus 2. The derivative of that is 3. So my derivative is denominator, derivative of numerator, minus numerator, derivative of denominator over denominator squared. Because my number in the numerator was a constant, this part becomes times a 0, which makes a big 0. So I end up with something like a negative 12. I think you had a homework problem that actually worked this way over that. It's not a super tough problem. It's a quotient rule problem. As long as you remember the quotient rule and you know the steps, it's pretty straightforward. Big chunk of it turns into a 0. So you end up, which is a negative 12 over 3x minus 2 squared. However, if I wrote this problem this way, instead of 4 divided by that whole expression, I wrote it as 4 times 3x minus 2 to the negative 1, then I could actually use a chain rule on this. It's not a quotient anymore. Times another 3. So the negative 1 down to the front would make the negative 4. I'm actually going to write that. So it would be like a 4 times a negative 1 times the 3x minus 2 to the negative 2 times a 3. And if you put all the constants together, That's going to make a negative 12 times a 3x minus 2 to the negative 2. Which is exactly what I got with the quotient rule. This is where students are kind of, some of you are going to be like, nope, it's a quotient. I'm not changing it. I'm just going to hit it with quotient rule. I don't need any extra concerns. Totally fine. Others of you are like, ooh, I hate quotient rule. Look how much nicer that is. Yeah, I'd rather do it this way. That's cool too. Sometimes, if inside the quotient is something that might need a chain rule, it's better to see if you can rewrite the whole thing. If I do quotient rule on number 8 the way it is, I'm still going to have to think about that with some chaining. Okay. Actually didn't think very much about when I pulled example number 8 out here, but it's together. Number 8 is definitely is more difficult than number 7 because I've already got that. I've got a sort of another layer of difficulty in the denominator. But if you approach number 8 as 1 times 2x minus 1 to the negative 1/2, right? A 2x minus 1 under a root and in the denominator, then I can chain rule a derivative out of that pretty easily. It's going to be a little messy. It's going to have a 3/2 power and then another times another 2. But I can get there. The product rule on number 8 is actually a little tougher than rewriting it as a chain rule. So every once in a while, turning your quotient, especially when you've got that constant. When you don't have a constant up here, it's not going to work as nicely. It'll actually be kind of messier because you'll just build a product rule around it. But a constant over an expression is a really nice scenario to rewrite and pop into a chain rule approach. All right. Our last two problems take us right back to a concept that we talked about early in this unit, the idea of writing a tangent line. Okay. Things to remember when we do a tangent line is we need a point, x1, y1. We need a slope, m, because ultimately our goal is, or an easy way to approach it, this is typically the easiest way, is if we can get a point and we can get a slope, and then we can write a point slope form equation. The layer on this problem is to get the slope, we're going to need y prime. We're going to need to write the derivative of each of these to find y prime. And to find the point, we didn't have to do this on the last homework problems, but we have to on here. We have to plug x into the original function to find the y to make the point.